Hello, and thank you for coming to my talk. My name is Chinmay, and I'm going to tell you about achieving high throughput and elasticity in a larger than memory store. This is joint work with Badrish from Microsoft Research and Ryan from the University of Utah. So a quick one-slide summary of our work. Multi-core optimized single-node key-value stores are emerging today, and they offer very high throughputs, as high as 100 million events per second, with faster being a perfect example. Now, a question that arises is the following. Can we retain such high throughput in the public cloud? This is challenging because of two reasons. The first is that we need to saturate servers within the hash index. And to do so, we need to avoid request dispatch and network bottlenecks. And the second is that workloads change and VMs fail over time in the cloud. Therefore, we need to support reconfiguration and migration while preserving throughput. So this talk is about Shadowfax, a distributed key value store built on top of Faster, which can service 100 million events per second per VM on Azure, 80 million events per second per VM during migration, and which spans DRAM, SSD, and remote cloud blob store. So I'm going to start off by talking to you about a state-of-the-art cloud key value store called Seastar. Consider a server VM with 4 vCPUs that's receiving requests over the cloud network. Seastar hash partitions records across vCPUs, and the idea here is simple. It avoids synchronization on records to maximize throughput. Every vCPU has a request dispatcher, which listens to a unique TCP port. This dispatcher picks up requests from the network and then routes them to the correct partition or correct vCPU. Because every vCPU does this, it results in an expensive shuffle at the dispatch layer. And this doesn't scale very well across vCPUs in terms of throughput. Now, one way to prevent this would be for clients to route their requests to the correct vCPU or owner. But this would require clients to open a connection to every vCPU and would result in quadratic connection state. Clients could avoid quadratic connection state by shuffling requests between themselves, but then this results in the same earlier problem and would not scale well. Now, another problem with this approach, with this partitioned approach, is that migration cannot be parallelized. The migration task has to be scheduled on the vCPU that owns the particular hash range being migrated. And it also causes blocking, head of line blocking for requests on that partition. So Shadowfax was designed to overcome all of these problems. It uses the following principles. The first one is partitioned request dispatch shared data, where vCPUs share a lock-free index, and all synchronization doesn't happen in software. It happens in the hardware cache coherence protocol. Because the index is shared, migration can be parallelized and hence does not block requests on hash ranges. Shadowfax has end-to-end asynchronous clients, which issue asynchronous batches of requests to amortize network overhead. And this works well for workloads with inter-request independence, for example, click counts, heartbeats, etc. Shadowfax has a novel mechanism called asynchronous global cuts, where it uses per server view numbers to represent hash ranges owned by a server. And using these cuts, vCPUs or cores can avoid coordination during migration ownership changes. Shadowfax also has a scale-out and hash migration protocol that leverages these global cuts that's parallel, deadlock-free, fault-tolerant, and cancelable. For this, please refer to the paper. It also spans main memory, local SSD, and shared remote storage, which allows only hot records to be transferred during migration. For the cold records, pointers are sent out, and these are lazily cleaned up during compaction. So let's look at the first problem that Shadowfax solves, that of avoiding cross-core coordination at the server. We make an observation that shared memory is actually good for skewed workloads because you can serve hot records in parallel. So Shadowfax uses a single instance of lock-free faster. And the advantage is that all record synchronization happens using compare and swaps or lock-free operations. And hence synchronization is at the cache coherence layer. Request dispatch is partitioned. There's a dispatcher per core, which listens to a unique TCP port, each vCPU. Now, in order to keep servers saturated at the index, Shadowfax also uses a novel client library. So client vCPUs open sessions to server vCPUs. Requests are async and are enqueued inside these session buffers. And they are pipelined and transmitted in batches to the server vCPU. And this happens on every client vCPU for every server vCPU. So there's no quadratic connection state. Also, because of this cleanly partitioned dispatch layer, Shadowfax can actually leverage hardware accelerated transport using SmartNICs. For more information about this, please refer to our paper. Now, the second problem that Shadowfax solves is that of avoiding cross-core coordination during migration. So in Shadowfax, when a migration occurs, it changes a server's ownership, the set of records it owns, and this is known as a view change. Now, one problem here is that you need to retransmit operations that were issued after the view change to the new owner of a hash range. And suppose you were to try to scale out this view change across cores, it can become a serial bottleneck and lead to cores idling. So in Shadowfax, what it does is that it allows each core to independently observe a view change. And this is known as an async cut. This is not novel. It's been around for a while. The cool thing about Shadowfax is that this async cut actually becomes a global cut across all sessions that have been open to the server. And so Shadowfax pushes these global cuts out to clients. This avoids cross-core coordination across client vCPUs and allows clients to reissue requests to the correct owner. The final problem that Shadowfax solves is that of migrating records on SSD. So in faster, records can actually sit on SSD, and migrating these records can slow down migration because of I/O. So what Shadowfax does is it periodically flushes these records to a remote blob store. And during migration, it constructs pointers in place to these records and sends it out to the new server. And these are then lazily cleaned up, which helps accelerate migration. Cool, so now time for some eval. This graph here presents Shadowfax's thread scalability. So this was for a YCSB-F workload, and there are three configurations: faster scalability, Shadowfax's scalability with the network stack, and Shadowfax's scalability without acceleration. And you can see that Shadowfax retains faster's throughput and saturates the index. This next graph compares Shadowfax with Seastar. It has a third configuration where Seastar's index operations are disabled. And this effectively benchmarks, the throughput of the shuffle layer. And you can see that Shadowfax is 8.5 times faster than Seastar. Cool, with that, I come to the end of my talk. Here's a one-slide summary again. We have really fast single node key value stores. We need to be able to retain their throughput in the public cloud. And Shadowfax is a system that actually does so. Thank you.